Hi everybody, welcome to another video. In the last video we took a look at what does the graph of f prime tell us about the graph of f. And in this video we're going to do something really similar, but instead of looking at f prime we are going to look at f double prime, so the second derivative. And so the question is, what does the second derivative tell us about the original function f? Okay, remember that the second derivative is the derivative of the derivative, and so if a first derivative is supposed to be talking about the speed or the velocity or a rate of change, then we can think about the second derivative as thinking about how is our speed changing, or how is the slope of the tangent line changing. Okay, so let's say we have a graph of f that starts out with a really positive tangent line. So maybe it kind of does this, where you have a really large value that is a positive tangent line. One thing we can think about is that when we talk about the second derivative, we might ask a question like, what happens if the derivative is getting bigger, or in other words, is the slope of your tangent line, is that getting steeper and steeper as you walk along, or what if your derivative is getting smaller and smaller as you move from left to right? Thinking about getting, you might say, less steep, but not really. It kind of depends on which direction you're going. And so if we start out with a tangent line that is like this, that's really steep, positive, we could ask a question like, what does it look like for the tangent line to get less and less steep? Okay, so think like further in the negative direction. If your tangent line is going to get less and less steep, then f is going to kind of level out like this, and your tangent line is going to go from being a really large positive value at the beginning to now being not quite as high of a positive value, and eventually you might even get your function to be something like this, where it kind of levels out, where your tangent line is not even positive anymore, or I should say the slope of your tangent line is not even positive anymore. Now the slope is 0, and then if we think about the slope as continually getting lower and lower and lower, or smaller and smaller, then eventually f might kind of go and do something like this, where eventually your tangent line is actually negative. So this actually represents a situation where f double prime is negative, because what's happening here is that our derivative is going down more. As we talk about, the second derivative is describing how your first derivative changes. Well, your first derivative is changing by getting further and further and further negative, or by getting smaller. There's a phrase we typically use for a graph that looks something like this, and we're going to talk about something called concavity. Maybe you've heard of concavity before, but this graph is an example of a situation where we have something that is concave down, and we had f double prime was negative because f prime gets smaller. Let's say gets smaller. And so to get smaller means eventually getting further and further negative. And then we could have another situation where f prime, kind of the opposite of that, where f prime is going to get bigger and bigger and bigger, okay, as you go along from left to right. So if f prime is going to get bigger and bigger and bigger, that's going to be a situation where f double prime is actually going to be positive, going to actually be greater than 0. Let's think about kind of what a situation like this would look like. Let's say you start out with a derivative that is equal to 0. So you have a horizontal tangent line. What it means for f to get bigger is as you go from left to right, your derivative, or your slope of your tangent line, gets more and more positive, gets higher and higher. And so really, if you think about what that means for f is getting steeper and steeper in the positive direction, something like this. Okay, but this is not the only situation that we could have where f is getting bigger and bigger. If you think about kind of starting all the way from the left, what if at the beginning f prime wasn't equal to 0? What if f prime was really far negative, something kind of like this, right? Where if you have the tangent line like this, at the very beginning, the tangent line looks like it has a really pretty steep negative slope. And for the slope to get bigger and bigger and bigger means that at some point the slope of that tangent line needs to kind of level out, okay? And kind of level out and go from really far negative to sort of negative to 0 to sort of positive to really positive. and I don't necessarily mean to have two different pieces in here. They're supposed to kind of represent the same. But the idea being that as you walk along from left to right on this graph, your tangent line is getting bigger and bigger. The slope of your tangent line is getting bigger and bigger and bigger. Probably should have given a little space in between these to kind of denote that they're different. These aren't the same picture, but this bottom situation is a situation where we have, we would call this concave up. And so the idea of concave up, to kind of summarize, concave up, sometimes we use the abbreviation CCU, kind of looks like a bowl, essentially. Or some people would say it kind of looks like a smile, because not only is it helpful to know kind of what the graph looks like, but it's also helpful to remember kind of which situation represents what, because we're going to see some examples where there's a lot of information to keep track of. We're going to talk about maximums and minimums, increasing, decreasing, concave up, concave down. Where do you have critical points? Where do you have other points? There's a lot of different information going on. And so it's helpful to be able to remember some things too. So I don't know if you're the kind of person who likes to have kind of a cheesy acronym to help you remember some things, or some kind of cheesy wording. And so when you have a situation where you have a graph of f that's concave up, that means that f double prime is greater than 0. Okay, and here's the kind of the saying to help you remember what goes with what, is that f double prime here is positive. Okay, and what do positive people do? Well, they smile, you know, so your graph looks like a smile over here. So positive people smile. So when f double prime is positive, that means that f is going to be, in that spot, is going to be concave up, and that means it's going to look like a bowl or a smile like this. Well, okay, great. Well, when f is concave down, as an abbreviation over here, this is a situation where we said f double prime is less than 0. That's negative. Okay, well, what do negative people do? Yeah, they frown, right? So there's a frowny face. So f double prime is negative. That means that your graph is going to kind of look like like an upside down bowl, or like a frowny face like that. Okay, so if we know how f double prime is behaving, then we can understand what is happening in the graph of f. Now, sometimes in some functions it's really hard to find f double prime if you have different chain rules and product rules and quotient rules and all those things thrown together. But in some functions, it's easy to find f double prime. If you have polynomials or something like that, you're just using a power rule. And if you look at f double prime, and it's hard to see how the graph of f might be behaving, you can understand more about how f is behaving based on the value, and when I say value, just like in the last example, last video, I don't necessarily mean what specific number you get. I more just mean a negative or a positive. Do we get negative or positive for f double prime? Okay, so by the way, you don't always have the whole entire smile or frown. Sometimes you only have like this little part right here, and you got to kind of think about, well, if you only have that little part on a graph, is that piece, that interval, is that concave up or concave down? So let's look at an example. Here's just a random graph on here, and I could say something like, so let's go like this, and I could say something like, where are there zeros? Where is this graph increasing and decreasing? Where does this have maximums and minimums? Or another question we could ask is, where is this concave up and concave down? And that can be a little bit tricky to be able to just look at a graph and see exactly where that happens. Okay, so if you look at this first piece, the first piece, does this look more like a smile or a frowny face? Well, it looks like a frowny face. So this piece right here is concave down, and at some point in here, there's a point somewhere. I don't know exactly where it is. We'd have to go find f double prime of this function to actually find a point in here where f double prime switches from being negative, because right over here, now in this piece, that looks like f double prime is positive. There is some point in the middle there where f double prime, assuming this is a continuous function at least, there's some point in there where f double prime is equal to 0, and it switches concavity from being concave down to concave up. Okay. By the way, concave down and concave up are kind of like talking about increasing and decreasing. We really only talk about concave down and concave up on an open interval. Okay, so not really even a closed interval, because technically at this point right here where f double prime is equal to 0, this is not concave up or concave down at that point. It's kind of in transition at that point. But then if you look at this graph over here, again on the end there's this kind of piece right here where that looks like more like a frown, and so there's another point in here somewhere where your graph switches from concave up to concave down, and where at the very end there you're going to have f double prime being less than 0, you got to find some point in here again where f double prime is going to be equal to 0, and it switches, the f switches from being concave up to concave down. So these are really hard points. These can be really hard points to just be able to look at a graph and identify where they happen. What's really going to help us out is to look at f double prime of x and find where f double prime of x is equal to 0, and then look at the intervals around those. It's actually a lot like we did in the structure of the last example, where we said let's find where f prime of x is equal to 0, and then look at what happens on either end of the interval there to decide where f is increasing or decreasing. This time with f double prime, when we look at the interval of where f double prime is positive or negative, we're not finding whether f is increasing or decreasing, we're finding where f is concave up or concave down. That actually brings up an interesting point. One thing I wanted to mention, but I kind of forgot about over here, when we talk about concave down, concave up, notice concave up and concave down don't really have anything to do with increasing or decreasing. When we look at concave down over here, there is a part of the concave down graph that is an increasing part of a function, and then there is part of the concave down graph that is decreasing. For the concave up graph, there's part of the concave up graph that is decreasing and part of the concave up graph that is increasing. So you can't just tell whether a graph of f is increasing or decreasing by knowing whether it's concave up or concave down. That is not enough information to be able to tell. We need more than that. Okay, we'll see that in a couple examples in the next video, but again, we're just kind of using f double prime here to try to tell us about concavity of f. With this example, one last piece of vocab before we look at one example to wrap up this video. These points where f double prime is equal to 0, technically our book just says the points where our graph changes concavity from concave up to concave down or concave down to concave up. These have a title, a definition, just like how we talked about critical points as being where f prime is equal to 0 or where f prime does not exist. When we talk about changing concavity from concave up to concave down or vice versa, these are often called inflection points. Inflection points. Okay. So let's go ahead and take a look at one example here to wrap up. I'm going to say something like find all inflection points, and I'm going to abbreviate it if that's okay with you. Find all inflection points and all intervals where f is concave up and concave down. Okay, and so here is your function. F of x equals x to the fourth minus 4x to the third. So go ahead and take a minute, see what you can do with this. Okay, and when you're finding inflection points in concavity, you should be finding a second derivative. So first of all, you need to find a first derivative. This is 4x to the third minus 12x squared. Find the second derivative, which is 12x squared minus 24x. And remember what we said before is take that derivative and set that equal to 0, that second derivative there. This is kind of nice. You can factor out a 12x again. So 12x, and you're left with an x minus 2, and this is equal to 0. And so you get something like x equals 0 and x equals 2. Now, this is where we're going to add a little bit to the structure we had on the last example. There are inflection points at x equals 0 and 2. But then the question is, where is f concave up and concave down? This should look very similar. We're going to do something like we did in the last video. But instead of looking at f prime, we're going to look at f double prime. F double prime is equal to 0 at both of those points. And the question is, before 0 and between 0 and 2 and after 2, is f double prime positive or negative? I think if you pause the video and go find these values for a second, I think what you should find is that between negative infinity and 0, you get a positive for f double prime, you get a negative and then a positive, and you can think about what does that tell you about f. F should be concave up, then concave down, then concave up. Okay, hope you've enjoyed the video.